new, something useful for chemistry. If you go back into our journey where we started with atomic structures, the Bohr's model, and all that stuff, from nuclear chemistry to Big Bang theories, a lot of stuff was introduced for the first time in the class. And we talked quite extensively about the atomic properties, the uh, chemical bonding, especially the valence bond theory and the molecular orbital theories to explain some unusual features of chemical bonding. We talked about symmetries of the orbitals. We talked about symmetries of the molecules, the geometries of molecules, point groups. So the list goes on and on. I mean, quite a lot of stuff we have covered over a period of about 14 weeks. So I hope we have learned something interesting about inorganic chemistry. And those of you who have been paying close attention to the class, you may have noticed that I have been bringing lots of examples of inorganic molecules in explaining point groups or the symmetries. So just to give you an idea about the plethora of inorganic compounds that are possible with the combination of several elements in the periodic table. So this class being the last one, we're not going to introduce new topics today. Instead, what we're going to do today is to get any clarification for the materials that we have been going through and take any questions from the class. And, so we told you already the exam will be on Monday as per your wish, that it will be available next Monday morning between 8 and 10 p.m. So you can pick up any time of your choice, answer the questions within about a couple of hours time. I tried to make the exam a little simple. So just only 25 questions, just like the previous two exams. That will be cumulative. All right. So this time, the floor is open for any questions. Now, before I take the questions, I just want to make sure that you all have been getting all the lectures on the Canvas, right? Whatever we do in the class. And I want to publicly thank Mr. Gurveer Singh, who has been instrumental in recording these videos and, giving to me on time so that I can put it on the Canvas. So I would like to shout out for Gurveer for all the hard work he has done in keeping track of all these lectures. Thank you, Gurveer. And we sincerely appreciate all your help.
No problem.
All right, so the floor is open for questions. Anything that you want to review or anything that needs additional clarification?
Professor, I was wondering if you could go over the Slater's rule, or a little bit, like do an example of it, because it's been a while since we did it.
Okay, you can pick up something and then I can work on it. Do you have an example?
Sulfur, for sulfur.
Sulfur? Which electron of sulfur? Do you have a specific electron in mind? So let me write down the sulfur electronic configurations: 1s2, 2s2, 2p6, 3s2, 3p4. Right?
The 3s2.
3s2 electron?
Yes.
Okay. So when you're looking at s or p electrons, we said all the electrons in the same shell contribute about 0.35, correct? Remember the notes? So if you look at the outer shell, there are 6 electrons. If you are looking for one of the 3s electrons, then there are 5 other electrons that are exhibiting repulsions of this electron. So we start with 5 electrons times 0.35 plus, then we have 8 electrons in the shell below, And we said n-1 shell electrons contribute about 0.85 to the overall charge. So that will be 8 times 0.85. And all the electrons in n-2 and below contribute 1.0 for the charge. So there are 2 electrons that will contribute 1.00. So that will be your shielding. That makes sense, Gurveer? So
Yes.
can you tell me what this number is? Five times 0.35 times plus 8 times 0.5 plus 2. Or somebody else also can jump in and tell me what that value is.
I think it's 10.55.
Is it 10.55? Is that what everybody gets? Just want to get a second opinion on this.
Yes, that's what I got too.
Great, excellent. Okay, so that's your shielding parameter, sigma. So if you want to find the effective nuclear charge, we already know effective nuclear charge is the atomic number Z minus the sigma, which is the shielding parameter. So if you look at now, the Z is 16 for sulfur minus 10.55. So that's about 5.45, right? So the 3s electron of sulfur experiences only 5.45 positive charges, although there are 16 protons in the nucleus. That makes sense? So if somebody wants to know what is the energy of this electron or the ionization energies, right? So we can calculate that because the energy is proportional to Z squared over N squared, where Z is the Z effective. So this will be the E is proportional to Z squared, which is 5.45 squared divided by N squared, where N is the principal quantum number of the electron under consideration, which in this case happens to be 3. So that will be 3 squared. And we also said we always compare those energies to the energy of the 1s electron of the hydrogen, which is proportional to 1 squared over 1 squared, and which we know is 13.7 electron volts. So taking the ratio on both sides, we should now then be able to calculate the energy of the 3s electron of the sulfur. As we just take the ratios on both sides, we already know everything except the unknown is the energy of the 3s electron from which we can calculate. That makes sense?
Yes, thank you.
No problem. I'll just stay away so that you can copy the notes there. But other questions?
I have one question.
Sure.
Is that 13.7? That's for the hydrogen, right?
Correct.
Okay, I just want to make sure.
So basically what happens is, if you want to shortcut all this process, you can also say, if I can erase this part of the board, so essentially the energy of the 3s electron of sulfur will be basically 5.45 squared divided by 3 squared times 13.7 electron volts. Clearly, it's going to be much higher than the energy of the 1s electron of hydrogen. So in other words, it is more difficult to remove the 3s electron of sulfur relative to removing the 1s electron of hydrogen, because it's more than 13.7. That's the reason why sulfur never forms a cation. It always forms an anion, especially when it reacts with elements whose electronegativity is smaller than that of sulfur. Does that answer your questions, Hannah?
Yeah, that answers the question.
Okay, great, excellent. Other questions? One more thing I just want to share with you, the university just sent us a note that the university has entered an agreement with Chegg. I don't even know what that company is, but apparently a lot of some of the students, not everybody, some students are using that. So the university has asked the Chegg to retain the records of all the students who come from Rowan and should be able to provide the information back to the university within 3 days of the completion of the exam. So my strong recommendation is stay away from those spurious sites. Okay, you have all the information, you have the lectures with you, you have the notes with you, have the textbook with you, you have everything. Nobody is even proctoring your exam. So please follow the academic integrity. So that's the email that I just got yesterday from the provost office. Because they don't want to have any academic integrity violations for many of the students here. So don't tell me I didn't know that. We didn't know that. So as per the university regulations, posting questions or sharing the questions with anybody else other than the class or getting advice from others, even from remotely, is considered as an academic integrity violation. Just want to let you know. Not that anybody is doing in this class. This class has a clean record. But that applies not only to this course, but any course that you're taking on the campus. The university has an agreement with Chegg now to report academic integrity violations. All right. Other questions?
Can you go over the 18 electron rule one more time?
Sure, definitely. Just like the octet rule that we apply for molecules, complexes are stable when the total number of electrons, that is electrons from the metal and from the ligand, if they're all equal to 18 electrons, right? That those complexes are generally stable. Suppose if I take maybe a couple of examples, you can give me an example, perhaps I can use that as an example if that helps. I think we have done, let's take an example of WCN8 3-, right? I gave you a list of ligands that contribute 2 electrons, neutral ligands, 2 electron anionic ligands, and 4 electron anionic ligands, and finally 1 example of a 6 electron anionic ligand. Alyssa, you have that right with you?
I have it. I'm gonna pull it up now.
Okay, great. So the way we count these electrons essentially is we got to see this is an anionic ligand, right? What is the oxidation state of tungsten in this case?
+5.
+5. Right? So the total number of electrons of the ligands and the metal we have to count. So how many electrons are coming from here? There are 8 Cn minus ligands, right?
Mm-hmm.
So what do we say? How many electrons are coming from cyanide? Others can jump into 2. Hannah?
Isn't it 2 each?
2 each. So that's going to be 8 electrons from this, correct? And how many are coming from the tungsten 5+? What is which group is tungsten in? Just look at the periodic table. The chromium, molybdenum, and tungsten are the same group, right? That's a group 6. So there are 6 valence electrons. So if you have 5+ state, that's going to be 1 electron from tungsten. Right? So how many we have now? This is going to be 16 plus 1 is a 17 electron complex. We also have done some examples of this too. I remember, we'll take one more example of this. Suppose if I were to say there is a complex of cobalt carbonyl. If it has 18 electrons, what is the charge on this complex? I don't think we did this example, but since you are asking, there are so many complexes that we can do. Here, we're trying to understand what is the charge of this complex, given that this has 18 electrons. So for answering that, we have to see how many electrons are coming from cobalt, right? I'm sorry, not the cobalt, carbon monoxide. It's a neutral ligand, right? But it's a neutral ligand that donates 2 electrons. So 5 times 2 plus the number of electrons from the cobalt will decide what the charge is. We don't know what the charge on this complex is, right? So we will call this X here. And because we know this is an 18 electron complex, that should be equal to X. That should be equal to 18. So X now will be 18 minus 10, 8. So what should be the oxidation state of cobalt that will supply 8 electrons? For example, if you look at the cobalt electronic configuration, we all know cobalt is argon 3d7 4s2. Right? So clearly we have 9 valence electrons on the cobalt, but in this case, cobalt is only contributing 8 electrons. So how many electrons it must have lost?
1.
1 electron. So it must be a +1 complex. So this Z value is +1.
How come in the last example the cation it went by what group it fits into in the periodic table, but here the cobalt does not?
Well, the best way to do that is whenever you look at the elements, right, you have their electronic configurations readily available, right? Both tungsten has 6 valence electrons. Okay, tungsten is 5d4 6s2 configuration, so 6 valence electrons. Chromium has 6 valence electrons. So the highest valence state of chromium is 6+. So is molybdenum, because we have only total of 6 valence electrons. So when you are making the highest oxidation state of that metal, that cannot be more than the number of valence electrons. So for example, in the case of cobalt, the maximum number of electrons you can remove is 9, no more. But in general, what happens is elements after iron, they generally have very low oxidation states. Cobalt, for example, is either in 2+ or 3+ states in general. There have been some suggestions of cobalt being 4+ state, but that is being actively debated even today, because what generally happens in these transition metals is, as you remove the electrons, the energy of the d orbital keeps coming down. And to a point, if that energy of the d orbital falls below the p orbital of the anion that it is bonded to, then the electrons will jump from anion to cation. So that is how the valence state never exceeds 4+ in the cobalt here. But that's for a different discussion, but this is how we find out. Does it satisfy you?
Yes, that makes sense. Thanks.
Thank you. So the best way to write this exam is write down all those tables, right, next to you separately, so that you have what I call a ready reference guide right next to you. Instead of looking while you started the exam, the best thing is to write down all these equations, constants, and everything on a piece of paper right next to you. Similarly, point group classification table, right? That table, you should keep it next to you before you even start the exam. So if there is a question about point group classifications, you can immediately refer to that sheet and you be able to answer without wasting too much time. That makes sense to you? Is everybody okay with that? Okay. It requires a little time, but unless you practice, like when you do things over and over, things become very common to you. But for the first time when you're trying, it's always a good idea to have a reference note right next to you. All right, other questions?
Professor,
Yes.
I was wondering if we could go over something from the valence bond theory, like finding the state of hybridization.
Okay. Sure. Can you throw an example?
Maybe sulfur and sulfuric acid.
Sulfuric acid, maybe in sulfur. Okay. Okay, sulfuric acid, H2SO4. Okay. First thing is, before you find the state of hybridization of any element, there are a couple of things you need to remember. Number one is we need to write the correct Lewis structure of the molecule, right? And the second one is hybridization applies only to central atoms, not to the terminal atoms. Central atoms are defined as the atoms that are connected to 2 or more atoms. Okay? That is the definition of a central atom. So without wasting too much of our class time, let me write down the correct Lewis structure of the sulfuric acid. So okay, that is your, so how many central atoms you have in this Lewis diagram now? So how many atoms in this structure are connected to 2 or more atoms?
Is it 3?
You are absolutely correct. You have sulfur that is connected to more than 2 atoms, and you have 2 oxygens that are connected to more than 2 atoms. All right. So once you identify, then let's say if I want to know what's the state of hybridization of sulfur here, right? So we have to find out what is the steric number of sulfur. Steric number again is defined as number of atoms connected to the central atom plus the number of lone pairs. Is this clear? So when you look at this sulfur here, it is connected to 4 atoms, not the number of bonds. Please understand this carefully. We're not counting the bonds, we're counting the atoms. Big difference. So it's connected to 4 atoms and no lone pairs. So the steric number happens to be 4. Am I clear? Similarly, if you look at oxygen here, the oxygen is connected to 2 atoms and there are 2 lone pairs. That's a 4 again. So the table that we use here, maybe that may be helpful for you. 2, 3, 4, 5, and 6. These are the possible steric numbers that you may get in Lewis structures. If it is 2, it is sp hybridization. If it is 3, it is sp2 hybridization. If it is 4, it is generally sp3. Sometimes you can also have dsp2, but that is very rare. Number 5 is basically sp3d. Number 6 is sp3d2. So once you identify that number, then the state of hybridization becomes very clear. So in this case, the sulfur and oxygen should have an sp3 type of hybridization. So if you have multiple choice of sp3d, sp2, or sp2, sp3, your answer should be sp3 because the steric number is 4. Am I making sense? Is that okay with you? Or you want me to do more examples?
Yeah, so just a clarification. You're saying that a central atom is connected to 2 or more atoms?
Right, that is the definition. Central atom is defined as any atom in the Lewis structure that is connected to 2 or more atoms.
So then, I know we asked for sulfur, but if we were to ask for one of the oxygens, since they're connected to 2 at least, the steric number would also be 4 for oxygen.
Correct, absolutely. That's what we said here, right? Both sulfur and oxygen have a steric number of 4, so their hybridization should be very similar.
Okay, thank you.
So for example, if you want to characterize this bond here between sulfur and oxygen, that is an sp3, this is an sp3, so it's an sp3 bond.
Okay, thank you.
Good. So that table is something that you may want to keep it and write the definitions. So the accuracy of any of your answers depends on how well you understand the definitions. What is a steric number? It's not the number of bonds, it's not the number of atoms. And when you're looking at the hybridization, you have to mix atomic orbitals in a way to give you this many number of hybrid orbitals. So if you want to get 4, you need to mix equal number, 1 of s and 3 of p. When you mix 1s with 3p, the resulting number of hybrid orbitals will be exactly 4. That's what you need to satisfy the bonding here. Making sense here, all right?
Yeah, that makes sense. Thank you.
Great. All right. Other questions? You see, as a teacher, I should be prepared with all the chapters, right? I should be more prepared for the final than you people are. I'm not sure of other people of whom I cannot see. I don't know if they have any questions. You can always speak up, folks. You don't have to turn your video, but you can definitely turn your audio on and ask any questions.
question?
Yes,
Could we go over possibly, sorry, an example with the molecular orbital theory?
sure. Uh, let's say I have, do you have an example maybe? I don't want to always write, like I would like to take it from you and then work it out. That would be much easier. This class, we are only dealing with homonuclear diatomic molecules and their anions and cations.
Yeah, so don't we just mostly with the molecular orbital theory deal with like H2, like
Oh, yes. Yeah,
B2, like that kind of stuff?
sure. Yes.
Okay.
But give me an example so I can work it out. Or if you want me to pick up one, I'll pick it up.
I don't mind if you pick up one.
You don't mind?
No, you can. I just don't really have one right now.
Okay. Let's say we have O2 2 minus. What is this anion called? O2 minus is called oxide. What is O2 2 minus?
Is this peroxide?
That's correct. Suppose if we ask you how many, what is the bond order and the number of unpaired electrons in this species? Okay. So we need to know what the bond order is. So how many bonds are between the two oxygen atoms in this molecule? And also, do we have any unpaired electrons? All right. So to answer that question, we need to first start with the molecular orbital picture of the O2 itself. Right. Remember in the O2, we said, we want to draw the picture for the molecular orbitals for the O2, and then we can work on what will be the case for O2 2 minus. Okay. So first start with the template of the neutral diatomic molecule, and then consider the charges later on. So if you do that, you get the 2s and the 2s of the oxygen and the 2p of the oxygen that is separate here. We have this. That is the template of the oxygen and the fluorine molecules. We have seen that. So this is the 1 sigma, 2 sigma star, 3 sigma, 1 pi, and 2 pi star, and 4 sigma star. So these are all the assignment of the molecular orbitals for this picture. So for a neutral oxygen molecule, the valence of oxygen is, each oxygen has 6 valence electrons, correct? Oxygen is 2p4, so 6 valence electrons. So if you start filling 2 oxygen atoms, that will be 2 times 6, 12 electrons. This is for the neutral oxygen. We'll come to the O2 2 minus in a second. So when you do that, 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right? So if you look at the neutral oxygen molecule for the O2, the bond order is number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals divided by 2. So if you look at that, we have 2 plus 2, 4, 4 plus 4, 8. So there are 8 electrons in the bonding level, and there are 4 electrons in the anti-bonding levels, 1 in 2 sigma star and 2 in 2 pi star. That divided by 2, so that is 2. So the bond order of neutral oxygen molecule is 2. Now consider adding 2 electrons to make a peroxide here. So where would those electrons go, folks?
Would they fill in the pi?
The 2 pi star has space for 2 more electrons, right? So the additional 2 electrons will go here and there. So that now changes the landscape for the O2 2 minus. the bond order now is going to be, there are 8 electrons in the bonding levels. Anytime you're adding electrons to an anti-bonding orbital, that weakens the bond. So we have added 2 more, so that makes it 6 divided by 2. So that is going to be 1. So the bond order is 1. And there are no unpaired electrons in O2 2-. Unlike O2 that has 2 unpaired electrons and magnetic, O2 2- is non-magnetic, no unpaired electrons, and a bond order of 1.0. Hannah, would that make sense?
Yeah, it makes sense. Thank you.
Good. Thanks for asking. Again, I think we will keep this video also. So if you want to go back and review what we have done, you can, you'll be able to do that as soon as Gurveer gives me the copy of this video. Questions? Other issues? I spent 2 hours this morning going over all the stuff we went over. I didn't know what questions you will be asking, right? So, and sometimes I forget myself what we talked about. So it was useful.
Professor, will there be any problems about the mass defect in the exam, like calculating it?
Math will be there, but it will not be overwhelming. Like, for example, if there is a question about effective nuclear charges, right? There's going to be some math, but I'm not going to ask you to derive the Bose equation there. Remember, we went over that in the beginning of the class, where we talked about Coulombic forces, centripetal forces, and trying to calculate the Bose-Balmer equation and all this. Those derivations will not be there. I just showed you just to convince you that these equations can be derived simply using physics. But to answer your question, no, there will not be any hard math.
I was saying no math. I was saying mass defect when the mass defect problems that we did.
Like what?
Like when you have the with the binding energy, that you can calculate it in joules or electron volts, like that kind of math.
Oh yes, yeah. If you're asking about the bond energies, right? Yes, that will be there. Basically, what happens is, let's say if I have a reaction of CH4 plus O2 giving CO2 plus H2O, right? So if you look at this one, how do you balance this equation here? It will be 2 waters and 2 oxygens, 4 oxygens, 2 O2. Let's say if I give you this, and I want you to calculate the delta H for this reaction from the bond breaking and bond making arguments. Okay. In all these questions, what we'll get is basically the delta H of any reaction is sum of the bonds broken, energy of the bonds broken, minus the sum of the energy of the bonds made. If your return by making more bonds is higher than the investment, which is to energy to break the bonds, then the reaction is going to be exothermic. So to answer that question, you need to first start with the Lewis structures of all the molecules. So that tells you how many bonds you have between the atoms. And if you're looking at oxygen, it's going to be O double bond O, and CO2 again, 2 double bonds between carbon and oxygen, and 2 single bonds of oxygen and water. So in all the questions, we'll tell you exactly the bond energy of the CH, bond energy of the O double bond O, bond energy of C double bond O, and bond energy of OH. So once you have this, you have to count the number of bonds. So the bond energies are always given in kilojoules per mole. So in this equation, I have 2. So you need to multiply that bond energy by 2. Similarly, if you have 4 CH bonds, you need to use 4 times the CH bond energy. Am I making sense here? So once you get that, and once you get this, we'll be able to do that. Let me also tell you at this time, in the Canvas exam writing, somehow the delta was not showing up. So it shows up as capital D. So please consider D as the delta. Similarly, the sigma comes up as an S. And there's no way I could change the font like you do that in the Microsoft. So Canvas has a weird text editor. So we're complaining about this, but until then, if there is a question like this in the exam, we will tell you that S means sigma and D means delta, okay? Is that what you're asking, Gurveer, or am I missing you?
No, that's what I was asking. Thank you.
Okay, good. Very nice. In some of the problems, you may also, we give you the delta H of the reaction and want you to find out one of the bond energies. So basically, once you have an equation, if it has 5 parameters, given any 4, you should be able to solve for the 5th one. That's the kind of simple algebra that we'll be using here. Other questions?
Professor, just a quick question about
Sure.
the problem we went over. The bonds made are just the products, right?
Correct.
And then the bonds broken are
Yeah, bonds broken are on the left-hand side. So you break all the CH bonds, you break the OO double bond, right? And at the right-hand side, you make 2 C double bond O's and 4 OH bonds.
Yeah, okay, just making sure. Thank you.
Yes, yeah. It's always good to ask for clarification. Great.
Can I ask another question, Professor?
Any number of questions, no problem. Sure.
So can you go over why iron is the most stable element? Like, I understand that all the elements, iron has the largest binding energy per nucleon.
Right.
And all the elements on the right
Mhm.
tend to break down and make iron, while the elements before iron tend to fuse together to make iron, right?
Right.
So, like, could you go over that? Why is that?
Okay, it just works out that the math of this, right? So what happens is when you plot the binding energy, again, remember the binding energy is calculated based on the mass of the nucleide, right? Minus the masses of the sums of protons and neutrons involved in the formation of the nucleus. So whenever there is a difference, obviously there is always a difference, right? That difference basically defies the law of constant masses, right? That kind of defies the principle that mass cannot be created or not destroyed, but in nuclear reactions that can happen. In fact, the energy comes out because of the difference in the mass. So when the mass disappears, it comes in the form of energy. So we take that energy and divide that by the number of nucleons. Number of nucleons basically is the number of protons plus the neutrons the iron has, okay? So what's the atomic number of iron?
26.
26. Right? Suppose if I have a 56 iron 26. Okay. So what this tells you is you have about 30 neutrons and about 26 protons in the nucleus. The masses of the protons and the neutrons are well known, well established. And the masses of the isotopes are also well established. So we take those masses, and any difference there basically converts into 931 million electron volts for one atomic mass loss. Okay. Remember the calculations we have done in the past. So when you take that energy and divide that by the total number of nucleons, which is 56 here, basically what happens is that happens to be very high for the case of iron. So if you look at the elements below iron, they're like this, and above iron, they go like this. Okay. So please keep in mind that although iron is the most stable nuclear on this planet, on the grand scheme of things, when you look at the entire universe, the amount of iron we have in the universe is not as high. It's much less than 1%. The majority of the universe is still hydrogen and helium. About 89% of it is hydrogen and about 10% of it is helium. So the iron is, or all the elements put together, is very small. But between those elements, which are relatively low abundant, iron is the most stable nuclear. So elements left of the iron tend to undergo nuclear fusion. That means they increase the nuclear mass until they reach this. Similarly, elements on the right-hand side of the iron go through nuclear fission because the binding energies are not favorable for either elements below iron or above iron. That makes sense, Guru?
Yes, thank you.
Sure, no problem. That's what we discussed in the class, and we have done some examples, right? How to calculate the binding energies per nucleon. I think we've done a couple of examples in the class, I believe, if you go back to the lecture notes in the past. If there are no other questions, let me ask you guys some questions. Some kind of a friendly feedback. So how do you find this course? Is it useful?
I
I
think
like-
yeah, go ahead.
Yeah.
No.
go ahead.
I was just gonna say, like, I think it's interesting. I don't know. I've never really thought about all the other elements just because we're so ingrained with Orgo, and
Right.
so I just never really gave them much thought, and only knew where like a couple of them were on the periodic table, but didn't know why they were there, and what that actually meant. And so I feel like I've learned a lot more about like basic chemistry
Right.
in upper level course, which was kind of cool.
Thank you. Others can weigh in too.
I thought it was really interesting learning about how inorganic, inorganic chemistry relates to medicinal chemistry.
Mhm.
That really interested me, especially the whole lithium example where that you sold us at the beginning of the term, how they put lithium in Sprite and everyone got happy.
Yes. 7-Up. Yeah. Yep, that's
Yeah.
right.
Yeah, I thought that was really cool.
Great. I mean, that's something that I have done for the biochem majors who may or may not be taking the advanced inorganic chemistry. So some of you are not required to take advanced inorganic chemistry. So, and nowhere else you will be introduced to inorganic component of the medicinal chemistry. So I thought I will spare 1 or 2 lectures on that and then provide you some information.
Will we be working on any of that in advanced inorganic chemistry lab? Because I'm taking that next term.
In the lab, you'll be making some platinum complexes. Remember the cancer complexes, the cancer stuff?
Yeah.
The cisplatin, right? Some platinum complexes we will be working on. You'll be making some copper complexes. You'll be making some cobalt MIMT complexes where you will see the effect of linkage isomerism that we talked about in the class. You will be doing that lab there. You'll be making your compounds. So a lot of work on complex formation, like DMSO, right? Dimethyl sulfoxides. I mean, you all heard about that in organic, right? And that can also make complexes with mercury, cobalt, copper, nickel, platinum, rhodium. So you'll be making all those wonderful complexes, seeing the colors of the complexes, getting the spectra of the complexes, UV visible absorption to see where exactly these complexes absorb light. And you will also look at the IR spectrum to see how the bond vibrations change when the linkage changes in the ligands. So there's a lot of interesting stuff you'll be learning. Just purely observation, you know, like you'll be making complexes and doing that stuff. And of course, we will also go a little bit deeper in the lecture on why some complexes are colored and why some are magnetic, why some are not magnetic, why some are kinetically inert and why some are extremely active. Some complexes are very active, some are not. So we kind of dwell into the theory, what we call the crystal field theory. So that's, yeah, yes, definitely whatever you have learned in this class, we will be building on that. We will not talk about isomerism or any of that stuff in advanced inorganic. We'll just go back straight to the chemical bonding. We draw a line between the metal and the ligand, right? But we have not talked about what that line really means. Hybridization, unfortunately, doesn't work in coordination complexes. So we'll talk about different bonding models. That's an interesting stuff, but we'll leave it to the next semester. Other comments on, can somebody comment on the pace of this course? Is it too fast, too slow, or about right?
I think you moved at the right pace for like the learning of all the new material. I was also just gonna say I thought it was a really interesting course and a different perspective. So
Right.
Yeah, I think it's the same. It was a really good pace.
Yeah, it was really good. It wasn't like too fast where I felt like I had to catch up, but it also wasn't too slow because it was like a lot of new stuff. So it was like right amount of time.
Well, this is the course that introduces you to the entire periodic table, right? We didn't leave any of that stuff. If you really watched my lectures very carefully, we have touched upon almost the entire periodic table, the rare earth metals, the actinides. We talked about the nuclear transformations. We talked about coordination complexes of the transition metals. We looked at the main group chemistries, the lead, antimony, tin. Remember we talked about this inert pair effect a long time ago. When we talked about inert pair effect, I introduced elements like bismuth, indium, lead, right? And thallium. So you don't get that kind of information in other courses. So this is one thing that comprehensively talks about periodic table and gives you some confidence. Your Argo stuff is good if you are just putting your career around pharmaceutical industry. But if you want to go to mining, there's a huge amount of money to be made in mining. And mining involves cocktail of all the elements in the periodic table. You have iron, you have silicon, you have aluminum, you have molybdenum, and a lot of companies around this area. There is a company which is situated about 15 miles from Rowan University called American Flux and Metal. They routinely hire students from Rowan, especially people who have taken my class, because 25 years ago, I started emphasizing the importance of periodic table in the chemical learning. And this company loved it. And all their employees, chemists and engineers, are from Rowan. And they're doing very well. They make molybdenum metal. They sell it to Japan and make a lot of money. You may not even know this, right? That there is a company that makes tons of molybdenum metal 15 miles from Rowan University. And they are the major exporters of molybdenum metal to Japan, because molybdenum is used extensively in the automobiles.
What's the company called again?
American Flux and Metal. You can Google them.
There's a question in the chat, and
I'm sorry, I'm not watching the chat.
It's okay.
Sorry, let me see. Chat. Oh, sure, definitely. There's a question about hard and soft metals. I think we talked about hard and soft in terms of polarizing and polarizabilities, right? So the hardness or softness generally is proportional to the ionization energy. Higher is the ionization energy, more hard the atom is. Of course, to be very technically correct, you got to say it is IE plus AE of 1/2. But I'm leaving all that and just giving you, because AEs, those electron affinities are very small. So to a first approximation, the hardness is related to the ionization energy. So in general, what happens is, if I have a periodic table, hydrogen, lithium, sodium, potassium, rubidium, and cesium, right? So that's the group 1A elements. As you go down the group, the size increases and the ionization energy decreases. When the ionization energy decreases, the hardness also decreases. In alternate way, you can say that softness increases. So elements become softer when you go down the group. When you go up, they become harder. Harder softness basically is related to how easy it is to deform the electron cloud around the nucleus. So if you look at hydrogen, the radius of hydrogen is very small. So that hydrogen exists like a near perfect sphere, and it's very difficult to distort the electron cloud. On the other hand, when you come to cesium, it is so huge that the nucleus is so far away from the valence electrons here. That distance is so large that the effective nuclear charge felt by the electron is so small. So it's very easy to distort this cloud. That means this atom is not nearly as spherical as the hydrogen atom. So this is soft here. That is true with all of them. If you go to fluorine, chlorine, bromine, iodine, and astatine, as you go down the group, the softness increases. In fact, you can also see this very clearly. You start with fluorine, which is a gas. Chlorine is a gas. By the time you go to bromine, it is liquid. And by the time you go to iodine, it's solid already. The reason for that is when you have a very soft atom, it gets polarized, and that leads to the creation of what we call instant dipoles. So the instant dipole-dipole interaction is what holds these atoms together. And that formation is related to the softness. So softer atoms are generally solids. You can see that in the periodic table too, right? You will never see gases when you go down in the periodic table. Most of them are solids. Does that make sense a little bit about softness? Somebody has any questions? Okay, thank you. And we also have to remember soft like soft, hard like hard, right? When you're making complexes, soft metals make strong complexes with soft ligands. Hard metals make strong complexes with hard ligands. Good. So the other thing I wanted to ask you is, in terms of the exams, are they fair? I mean, that's a tough question to answer because we don't have a good definition of what is fair.
I think they are fair, but since they're multiple choice, you cannot kind of get partial credit. That's the only downside of it.
Mhm.
Yeah, I think it's pretty fair. I think we go over so many problems in class that like at least like half of the exam isn't too bad, and then you know we can struggle for some of them, I guess.
It's good. So basically, an exam is not fair when you see questions in the exam that have no relevance to what we do in the class. That's what I call an unfair exam. Like, for example, I can do all the easy stuff in the board and ask you tough questions. Mind you,
gone over to some degree in class, or we had gone over to some degree in the lectures that you had posted.
thanks, Matt. That's nice to hear that. The other question sometimes I get from people is about the textbook. Was the textbook useful, at least in some aspects, if not completely?
I feel like the context and information you gave in class made it so I didn't feel like I really needed to use the textbook unless I wanted further explanation. But when I wanted further explanation, I would just talk to you. So I didn't really use it that much.
But those of you who tried to get some help from reading the book, was that useful?
We have a message in the chat. Somebody says that they use the textbook for certain things.
Okay, good. Yeah.
Also, like if personally for me, if I didn't get something, I rewatched the lectures on YouTube. Like that's what I did.
Okay. Yeah. For those of you who sometimes get frustrated by reading the textbooks, let me tell you that this book is written for graduate as well as undergraduate. So there are no separate textbooks for graduate or undergraduate. And one of the things what the authors have done, Du Schreiber and Peter Atkins, these are the two people who are architects of this textbook. What they have done essentially is to put all the information in each chapter. Sometimes it can be very confusing. Sometimes they just give an equation and try to work it out, but without even telling how these equations are obtained. For example, the atomic spectra equation, right? 1 over lambda equals Rydberg constant times 1 over n squared minus 1 over n2 squared. They never tell you where that equation came from. But that's not how I approach the course. I just showed you, even if it took a little bit of time, maybe 30 minutes, but at least you have an origin of how these equations come into existence. All right, so that's good. Good to hear that. I know I'm glad that we're all learning something. keep continuing. And then those of you who will be coming back to advanced inorganic chemistry, apparently for the next semester, it's going to be still virtual. All right. It's going to be like this. So I'll be uploading some lectures. Sometimes I'll be teaching. Unless Gurveer is taking the advanced inorganic, if you are taking, then I will request you to continue doing what you're doing here, recording the lectures. But if not, well, I'll try to find someone else.
I'm taking it, so I'll do it.
Oh, thanks. Good. Excellent. All right. So if there are no other questions, yeah, I see the textbook is helpful for certain people. Yes, it is. It has more information than what we generally go through, and it has more numeric information. Finally, before I let you go, how many of you have used the solution manual of this book?
I tried using it for the first, I think it was chapter, but I couldn't find it. The only one was like on Amazon and it was like $25. I was like, no, I'm not gonna do that.
$25 for this 5th edition?
I think so. It was about $25.
I don't know. I have no idea that they're still making money. They're not giving me any because I wrote a major portion of the solution manual on that. You could have, you might have seen my name too. On 2 editions I have worked. They stopped.
Great semester.
Hmm?
Thank you for a great semester.
Thank you all. It was all wonderful. And if I did say anything that hurt anyone's feelings, it was totally unintentional. So I beg for your excuse, but we try to, do our best here. And thank you all for your input. You made this class so lively, so wonderful. And I'll bet you this information will be so useful for you moving into the future. I still keep getting people who, are getting into jobs, telling me, thanking me, oh, we had no idea that we'll be doing all this in this company. And the managers are very happy that, you know a little bit about the periodic table. In addition to organic chemistry, if you put this chemistry in organic too, that gives you a broad perspective, which is what the company is like. In fact, you'll be surprised. One of my students who took this class went to a company, and then he had a question, came back to me, and then he solved the problem, and he just wanted to check with me a few things, and he got a patent. Can you believe that? Just using pure inorganic principles. I was so proud of him. He said, how come nobody thought about this? This is so simple, He looked into the literature, nobody talked about this. This is about the complexes, hard and soft complexes. So he had a task to remove magnesium from the fluxes. Then we knew that magnesium is a hard atom. So using a very hard anion like fluorine, he could selectively remove the magnesium from the flux. His boss was so happy. And then we had a joint patent on this. So, everything that you learn really helps you. Okay, if that is the case, I don't want to waste too much of your time. I know that you have so many finals coming up. And I'm still available, by email. If you need to sit down privately, please don't feel bad. Just send me an email and I'll be happy to set up a time with you to go over any concepts, any problems, or any confusion, or any clarification that you may need. All right. So I wish you all the best with your finals. Okay. Don't work too hard. Get the proper sleep. Stay safe, and enjoy the Christmas and an advanced Happy New Year to you all.
Thank
Bye
you.
now. Bye-bye.
Thank
See
you
you.
for this
Thank you,
class,
Professor.
Professor.
See you. Bye bye, folks.
Thank you, Chari.